Let's look closer at the chemistry of carbohydrates. Carbohydrates are also sometimes referred to as saccharides, sugars, or glycans. These are more or less interchangeable terms. From chemical perspective, carbohydrates are polyhydroxyaldehydes or polyhydroxyketones. Glyceraldehyde or dihydroxyacetone are simplest examples of respectively polyhydroxyaldehyde and polyhydroxyketone. Biological carbohydrates are built of the simplest building blocks, monosaccharides. Biological monosaccharides have a linear, non-branched carbon backbone consisting of 3 to 7 atoms. The monosaccharides can join together forming larger condensates. The small condensates containing up to 20 residues are called oligosaccharides. The condensate with a higher number of the residues are generally more than 20 are called polysaccharides. The monosaccharides, oligosaccharides, and polysaccharides can be chemically conjugated to other biomolecules such as proteins and lipids and are called glycoconjugates. Carbohydrates can also be not strictly carbohydrates, but could be chemically modified with other chemical groups containing nitrogen, phosphor, or sulfur atoms, which are referred to as phosphor sugars, amino sugars, or sulfur sugars. All sugars are named by using suffix "-ose". If one would see a compound which has suffix "-ose", it means that it's either sugars or they are close derivatives. The smallest building blocks of sugars, monosaccharides, are classified based on the number of carbons in the backbone and whether this is aldehyde or ketone. For example, glyceraldehyde and dihydroxyacetone are trioses. The glucose and fructose have 6 atoms in the carbon chain. They are hexoses. Likewise, glyceraldehyde has carbonyl group in the terminal position. This is aldehyde, so this is aldotriose. And dihydroxyacetone has a carbonyl group in the middle, in ketone position. This is ketotriose. Glucose is aldohexose and fructose is ketohexose. Besides that, it's important to define the position of carbonyl group. The convention is that the first atom, terminal atom, which is close to carbonyl group, is defined as number 1. Other atoms are carbon atoms are defined as in the second, third, and fourth, etc. position, starting from the first one. This way, the position of carbonyl group and other modifications could be unambiguously defined. For example, in fructose, carbonyl group in the second position. So by standard nomenclature, fructose is 2 ketohexose. Monosaccharides can also form stereoisomers. In stereoisomers, all the chemical bonds between each pair of atoms are identical, but they are configured with respect to one another in a different way in 3 dimensions. This could be easily illustrated by glyceraldehyde. If we imagine 3-dimensional structure of glyceraldehyde and place its carbon backbone vertically, the central carbon atom would be asymmetrical in the sense that all 4 groups bound to this carbon would be different. If the backbone is placed vertically and both carbon-carbon bonds would face outside the screen, the hydrogen atom and hydroxy group bound to this carbon could have two positions, two dispositions. One is hydrogen on the left and hydroxy on the right, or hydroxy on the right and hydrogen on the left. And it's easy to see that these two molecules are very similar but not identical. They are in fact mirror reflections of one another, and they are different as the pair of right and left gloves. There is a convention to define and depict the stereoisomers of sugars on the flat screen, on the flat paper, using Fischer projection convention. In Fischer projection, the glyceraldehyde is imagined to be a three-dimensional molecule placed like it is shown on the left, and then this is just flattened to the screen. If a hydroxy group appears on the right side, so this is called D or right or dexter isomer of glyceraldehyde. And if a hydroxy group appears on the left, this will be left-handed or levo in Latin, stereoisomer of glyceraldehyde. Such asymmetrical atoms are called chiral centers. If we take monosaccharides with more carbons in the chain, they can have also D and L stereoisomers and could be depicted using Fischer projection formulas. As a convention, the first carbon in the carbon chain is placed on the top, and the last asymmetrical carbon, last chiral center, is placed in 3-dimension using convention of glyceraldehyde, and then flattened to the screen. This way, if hydroxy group appears on the right, this will be this monosaccharide will be referred as D isomer, and if it appears on the left, it will be referred as L isomer. As an interesting fact, almost all hexoses, like mannose, glucose, and galactose shown here, are D isomers in biological systems. By fixing the last chiral center using the Fischer projection convention, all other chiral centers are automatically fixed in 3 dimensions. They could be flattened to the screen like it was done with glyceraldehyde, and as such any monosaccharide could be depicted flat using Fischer projection formulas. The example is the epimers, the monosaccharides which are different with respect to one another only by the 3-dimensional arrangement, stereochemical arrangement of bonds around one chiral center. Mannose and glucose are epimers. They are different in only one chiral center, second carbon. Likewise, glucose and galactose are epimers. They are different in the arrangement around, stereochemical arrangement around fourth carbon. These epimers, in spite of minute differences, have completely different biological properties and metabolic fates. This could be understood considering that the enzymes that perform metabolic reactions with these sugars have a peculiar 3-dimensional organizations of their substrate binding sites. If one sugar would precisely fit active center of one enzyme, it doesn't guarantee that its epimer with slightly different 3-dimensional organization will fit the same well. And these are the interplay between 3-dimensional properties of sugars and the peculiar 3-dimensional properties of enzymes with which sugars interact in the biological systems defines the huge functional diversity of sugars. Monosaccharides are highly reactive molecules because of the carbonyl group. Majority of monosaccharides can undergo reversible intermolecular condensation in solution, forming the circular forms. In this case, carbonyl carbon undergoes aldol condensation with one of the hydroxy group is in the same molecule. And this results in formation of hemiacetal or hemiketal, depending on whether carbonyl group originates from aldehyde or from ketone. In this case, the hemiacetal or hemiketal carbon becomes yet another chiral center. This could be illustrated in the case of glucose. Glucose in solution will undergo reversible aldol condensation where the aldehyde group condenses with the hydroxy group at the fifth position. In this way, the circular ring is circular form is made with six-membered ring. If you imagine the ring flat and the 6 carbon sticking at the top, so then two configurations are possible at this new chiral center. First, the hydroxy group could be on the opposite side of the ring, and another configuration is hydroxy group on the same top side of the ring as 6 carbon. These forms are stereochemically different and are called anomeric forms. The hemiacetal carbon in this case is called anomeric carbon. And the two forms, left and right, with these different configurations with respect to 6 carbon and hydroxy group are respectively called alpha anomeric form and beta anomeric form. The anomers and alpha and beta nomenclature is applicable beyond glucose and is used to define different anomeric forms for other sugars. The majority of monosaccharides with number of carbon atoms more than 5 are present in circular form in solutions. The most predominant forms are 6-membered and 5-membered rings, and for convenience, naming convenience, they are referred respectively as pyranosis and furanosis, which refers to simpler organic compounds, 6-membered ring and 5-membered ring, respectively, locked by oxygen. For example, the alpha and beta anomeric form of 6-membered ring of glucose will be referred to as alpha D-glucopyranose and beta D-glucopyranose, respectively. The fructose, which is ketose, is predominantly present in solution as a 5-membered ring. Its two anomeric forms would be therefore referred to as alpha D-fructofuranose and beta D-fructofuranose. Different cyclic forms of monosaccharides in solutions are different configurations. Besides these different configurations, each of the circle configuration of the sugar could be present in turn in different three-dimensional conformations. The difference between configuration and conformation is that the configurations cannot be turned into one another without breaking covalent bonds, and conformation can be turned into one another without breaking covalent bonds. For example, the cyclic forms of glucose can be present in several different three-dimensional conformations. The two most abundant ones are left and right chair conformation. In the chair conformations, the left carbon will be facing top and the right carbon would be facing opposite side, bottom. In the right chair conformation, it will be opposite. These two conformations are energetically identical. However, there is an activation energy to transit between those because it requires changes in the orientation of the bonds. Another possible conformation is boat conformation, which is not shown here, which would be left and right carbon faces facing one side. The energetics of different conformations is different. So the chair conformation of glucose, for example, are more energetically favorable than boat conformations, and because of that, the chair conformations are predominant. Besides different stereoisomeric forms, different conformations and different configurations, sugars, monosaccharides, sorry, can also be chemically modified, adding to their diversity. For example, shown here is the different modification of hexoses. Hexoses like glucose, for example, can be phosphorylated at different positions, forming different types of phosphosugars. Some of the hydroxy groups could be substituted with amino groups, giving rise to a large family of amino sugars. Some of the positions could be deoxygenated, forming dioxy sugars, or could be oxidized to carboxy groups, giving rise to a large family of acidic sugars, or some more complex modifications are possible, combining several of these kinds. Altogether, in a summary, we could see that in spite of a simple composition, the monosaccharides are extremely diverse molecules. They are different in the number of carbons in the carbon chains. It could be trioses, tetroses, pentoses, etc. Could have different position of carbonyl group, giving rise to family of aldoses and ketoses. Could have a number of different stereoisomers, which is 2 in number of n, where n is the number of chiral centers. On top, they can reversibly circularize, making different anomeric forms and different forming circles with different number, cyclic forms, sorry, with different number of items in the ring. This can in turn have different three-dimensional conformations, and the monosaccharides can on top have different chemical derivatives.